Welcome. Today, we're diving deep into the world of Java concurrency, focusing on how ConcurrentHashMap revolutionizes thread-safe data structures. In modern software, handling multiple threads efficiently is crucial, especially for backend systems that demand high performance and reliability. We'll explore why traditional HashMap falls short in concurrent scenarios and how ConcurrentHashMap steps up to solve these challenges. By the end, you'll understand the internal workings, concurrency model, and key differences between these two essential Java collections. Let's start by setting the stage for why concurrency matters in real-world applications. HashMap is a go-to choice for storing key-value pairs in Java, especially when only one thread is accessing it at a time. Its design is optimized for speed and simplicity, making it perfect for single-threaded applications. However, as soon as multiple threads start interacting with the same HashMap, things can get messy. Race conditions, inconsistent data, and even application crashes can occur. This is because HashMap isn't designed to handle concurrent modifications, which is a common requirement in today's multi-core systems. When multiple threads try to read and write to HashMap simultaneously, the lack of synchronization leads to unpredictable results. You might see lost updates, corrupted data, or even infinite loops due to internal structure corruption. This is a major concern for backend engineers building scalable systems. The need for a thread-safe alternative becomes clear as applications grow and demand more parallel processing power. One common workaround is to wrap a HashMap with Collections.synchronizedMap. This approach adds a lock around every operation, ensuring only one thread can access the map at a time. While this does make the map thread-safe, it comes at a significant cost. Every read and write operation is now serialized, eliminating any chance for parallelism. Under heavy load, this leads to high contention and performance bottlenecks, making it unsuitable for high-concurrency environments. As applications scale, the limitations of synchronized map become more apparent. Developers need a data structure that allows multiple threads to operate in parallel without sacrificing data integrity. Enter ConcurrentHashMap, a collection designed from the ground up to handle concurrency efficiently. Its architecture enables high throughput and scalability, making it a favorite among backend engineers working with multi-threaded systems. ConcurrentHashMap didn't just appear overnight. It evolved as a response to the growing need for scalable, thread-safe collections in Java. With the rise of multi-core processors and distributed systems, Java developers required tools that could keep up with increasing concurrency demands. The design of ConcurrentHashMap reflects lessons learned from earlier synchronization strategies, offering a more nuanced approach to locking and data access. Development and refinement of ConcurrentHashMap have been influenced by many industry experts and engineers. From staff engineers at major tech companies to contributors in the open-source community, their collective experience has shaped the robust concurrency model we rely on today. Their insights into system design, microservices, and distributed computing have ensured that ConcurrentHashMap remains relevant and effective in modern Java applications. At its core, ConcurrentHashMap is a thread-safe implementation of the map interface. Unlike synchronized map, it doesn't lock the entire map for every operation. Instead, it uses a sophisticated locking mechanism that allows multiple threads to read and write to different parts of the map simultaneously. This design dramatically improves performance and scalability, especially under heavy load. Earlier versions of ConcurrentHashMap used segmented locking, dividing the map into multiple segments, each with its own lock. This allowed threads to operate on different segments in parallel, reducing contention and improving throughput. While Java 8 and later versions have moved away from strict segmentation, the principle of fine-grained locking remains central to its design. With Java 8 and beyond, ConcurrentHashMap introduced lock stripping and other optimizations. Instead of fixed segments, it uses a combination of node-level locks and CAS, compare and swap operations. This approach further reduces lock contention, allowing even more threads to access the map concurrently. The result is a highly scalable data structure that performs well under extreme concurrency. One of the key strengths of ConcurrentHashMap is its ability to allow multiple threads to read data without locking. Most read operations are lock-free, relying on volatile reads to ensure visibility of the latest data. This means that threads can access the map simultaneously without waiting, significantly boosting performance for read-heavy workloads. Write operations in ConcurrentHashMap are handled with care to maintain thread safety. When a thread needs to update a value, it acquires a lock only on the specific node or bucket being modified. This targeted locking approach minimizes contention, allowing other threads to continue working on different parts of the map. As a result, write operations are efficient and scalable, even under heavy concurrent access. ConcurrentHashMap leverages CAS, compare and swap, operations for certain updates. CAS is a low-level atomic instruction that allows threads to update values without locking, as long as no other thread has changed the value in the meantime. This technique is especially useful for operations like put if absent, where atomicity is crucial. CAS helps further reduce the need for locks, enhancing overall concurrency. By combining fine-grained locking with lock-free techniques, ConcurrentHashMap avoids the bottlenecks that plague synchronizedMap. Threads rarely block each other, even during heavy read and write operations. This design ensures that applications remain responsive and performant, even as the number of concurrent threads increases. Let's compare the internal workings of HashMap and ConcurrentHashMap. While HashMap is fast in single-threaded scenarios, it fails under concurrency due to lack of synchronization. ConcurrentHashMap, on the other hand, is designed for multi-threaded access, using advanced locking and atomic operations to maintain consistency and performance. This distinction is critical for backend engineers building scalable systems. In high-concurrency environments, performance is everything. HashMap with synchronization quickly becomes a bottleneck, as every thread must wait its turn. ConcurrentHashMap shines here, allowing many threads to operate in parallel with minimal blocking. This leads to better throughput and lower latency, which are essential for modern backend systems. ConcurrentHashMap is widely used in real-world applications where thread safety and performance are paramount. Examples include caching layers, session stores, and any scenario where multiple threads need fast, consistent access to shared data. Its robust design makes it a staple in enterprise Java development. For backend engineers, understanding the differences between HashMap and ConcurrentHashMap is essential. Choosing the right data structure can make or break the scalability and reliability of your system. ConcurrentHashMap provides the tools needed to build robust, high-performance applications that can handle the demands of modern users. Even with ConcurrentHashMap, there are pitfalls to avoid. For example, compound actions like check-then-act are not atomic unless explicitly handled. Developers must be aware of these nuances to avoid subtle bugs. Always consult the documentation and understand the concurrency guarantees provided by the collection. To get the most out of ConcurrentHashMap, follow best practices such as minimizing lock contention, using atomic methods when possible, and avoiding unnecessary synchronization. Proper usage ensures that your applications remain fast and reliable, even as concurrency increases. In microservices architectures, services often need to share state or cache data efficiently. ConcurrentHashMap is a natural fit for these scenarios, providing thread-safe access without sacrificing performance. Its use in distributed systems highlights its flexibility and robustness. While ConcurrentHashMap is powerful, it's not the only option for concurrent data access. Alternatives like copy-on-write array list or synchronized collections may be suitable for specific use cases. However, for high-throughput, low-latency requirements, ConcurrentHashMap remains the preferred choice. ConcurrentHashMap integrates seamlessly with the broader Java ecosystem. It's used in frameworks like Spring and is a building block for many open-source libraries. Its reliability and performance make it a trusted component in enterprise-grade applications. The Java community actively supports and improves ConcurrentHashMap. From detailed documentation to community forums and expert blogs, there's a wealth of resources available to help developers master its use. Staying engaged with the community ensures you stay up to date with best practices and new features. Industry leaders and experienced engineers share their insights on using ConcurrentHashMap effectively. Their real-world experiences provide valuable lessons on performance tuning, debugging, and scaling concurrent applications. Learning from their successes and mistakes can help you avoid common pitfalls. Consider a backend system handling thousands of requests per second. Using ConcurrentHashMap for session management or caching ensures that data remains consistent and accessible, even as multiple threads process requests in parallel. This real-world example highlights the practical benefits of choosing the right data structure. As Java continues to evolve, so too will its concurrency utilities. Ongoing research into lock-free and wait-free algorithms promises even greater scalability and performance. Staying informed about these advancements will help you build future-proof systems. Recap: HashMap is fast but not thread-safe, making it unsuitable for concurrent use. SynchronizedMap adds thread safety but at the cost of performance. ConcurrentHashMap strikes the perfect balance, offering high concurrency, scalability, and reliability. Understanding these differences is crucial for building robust Java applications. If you want to dive deeper, there are plenty of resources available. Official Java documentation, open-source projects, and expert blogs offer in-depth explanations and real-world examples. Continuous learning is key to mastering concurrent programming in Java. In conclusion, mastering ConcurrentHashMap is essential for any Java developer working with multi-threaded applications. Its advanced concurrency model, efficient locking strategies, and robust performance make it a cornerstone of modern backend engineering. By understanding its internal workings and best practices, you can build scalable, reliable systems ready for the demands of today's software landscape.